Hi again, everyone. This is going to be a lesson on laws of logarithms. So we're continuing our discussion of logarithmic functions from last time. And in the last video, we established what logarithms are. We did a couple of little problems, and we established some facts about logarithms that can help us simplify things. And I think we ended with a word problem involving logarithms. So in this lesson, we're going to establish more facts about logarithms. There's basically three big rules that are called laws. And towards the end, we might have kind of one more extra one. So I say there's three big rules, but we might actually see four rules today. All right, let's get started. So even though this lesson is going to be on laws of logarithms, I thought it might be a good idea to do a couple of warm-up problems first. So let's do this off to the side. I'm going to give you a few quick logarithm problems. I'm going to ask you to evaluate these. And when I say evaluate, I mean evaluate them without a calculator. We're going to do log base 3 of 9. Log base 2 of 2, log base 5 of 1/5, log base 100 of 1, and log base 3 of 1/27. So take a couple of minutes and try these, and you could pause the video if you'd like to try them, and then I will talk about them in a minute. All right, so we're going to answer these pretty quickly. There's not really a lot of work that you need to show for these or anything like that. You might be able to just do some of these in your head. Log base 3 of 9, I'm going to say that this is 2. The reason why I'm saying this is 2 is because I'm thinking of this as 3 to what power equals 9. So you want to be able to either do that in your head or write it as scratch work, where basically you are looking at a logarithmic expression and you're kind of translating it into an exponential expression that helps you solve it. This was saying 3 to what power equals 9. We know that 3 to the 2 is 9. Number 2, you could answer by using one of those facts from the previous section. You could say that because those numbers are the same, the answer is going to be 1. If you don't think of it that way, you might think of it as 2 to what power equals 2. 2 to what power equals 2, that would have to be a power of 1. And I don't think I'm going to write this for all 5 of these. Next one, you should get an answer of -1. Again, because you could think of it as an exponent. 5 to the -1 is 1/5. Number 4, we would use that fact from last time that says when you do a log of 1, you always get 0, no matter what the base is. For this last one, let's go ahead and write the let's write the scratch work. So this is 3 to what power equals 1/27. Excuse me. So I know that 27 is a power of 3. 27 is 3 cubed. So 27 is 3 to the 3. But because it's in the denominator, it would be a negative exponent. So this is going to be -3. Okay, so hopefully problems like that are not too bad. We can actually do these for you could imagine that we could come up with lots of different examples like this. So hopefully we can do those quickly. Now, let's get into actual laws of logarithms. Before we establish some brand new facts about logarithms, I want to remind you of one that we've seen previously. And we had 4 rules, and I want to remind you of this one. Log base a of a to the x equals x. And I guess, technically we said this is for any base a and any number x. Okay. And this makes sense because log base a is the inverse of a to the x. That's the whole point of logarithms. They're the inverses of exponential functions. So you could think of the log base a and the a to the x as canceling each other out and just leaving us with what was on the inside. X is the innermost thing. The log base a and a cancel out. The reason I'm writing this again is because we're going to use this to help derive some additional properties, and we are going to derive them, or in other words, we are going to prove them. 3 big laws about logarithms. So for the discussion that follows, we need a few letters. So we're going to start by saying let a be greater than 0, a is not equal to 1. Let a, b, and c be real, with a greater than 0 and b greater than 0. All right, so we've established this, so we can now work with these letters. So what we're going to do, I think, is for these 3 big rules, we're going to state the rule, we're going to prove it, and we'll do that for all 3. And then once we've gotten through all 3, then we can do lots of example problems. These ones are so big that they are called laws. So law 1 about logarithms says that a log of base a of capital A times capital B is equal to log base a of a plus log base a of b. And I'm going to put a box around this. There's going to be 3 of them, and this is our first law. And it's not immediately clear why this should be true. I mean, it's kind of like saying on the left side we've got 1 logarithm. On the right side we've got 2 logarithms. So it's kind of like saying you could take a logarithm and split it up into 2 pieces in this particular way. Or you could say that because equal signs work 2 ways, an equal sign is a 2-way street, you could look at it and say if you had 2 logarithms like this right-hand side, you could combine them, you could merge them into 1 logarithm like this left-hand side. So this could be useful in 2 different ways. So let's get to work on trying to prove this. In math classes, we do like to prove the big results. We don't prove everything, but we try to prove the big things that we're going to be using because we want to justify them. We want to not just know how to compute things, but we want to understand where they come from and why they are true. Okay, what we're going to do, a lot of proofs in math come down to interesting little tricks that people have discovered, and this proof uses a little trick of introducing some extra letters. We're going to introduce a lowercase u and let it be this part of the problem. And we're going to introduce a lowercase v and let it be this part. Whenever I write something with logarithms, I could also convert it into thinking of it with exponents. So I'm going to say that u equals log base a of a means that a to the u equals a. And this other one says that a to the v equals b. And that's going to turn out to be useful. We have, in order to prove this law, we would like to show that the left-hand side does, in fact, equal the right-hand side. And we can't just, plug in specific numbers. If we show that it works for, pick a number for A and B. If you just put in specific numbers and check that it works, that doesn't prove that it always works. We want to prove that it always works. So we're going to leave them as letters. we're going to try to show the left-hand side equals right-hand side. So let's start with the left-hand side and see what we can do. One thing I could do is I could rewrite it in terms of u and v. So I'm going to write a to the u times a to the v. Okay, so the reason why we might do that is because now we have, inside the parentheses, we have a to the u, a to the v, and there's a property of exponents, remember, that says we can add those two exponents and make this just a to the u plus v. Which looks a little bit simpler. Now, if you look at where we're at, I'm going to put an equal sign because we still need to go further with this. If you look at where we're at, we could actually use this fact from above. That's why I wrote it, to remind us of this fact. Log base a of a to the x equals x. Log base a of a to the something. It should just equal that something. This equals u plus v. By that fact above, we get u plus v. Is that what we wanted? U plus v? Well, what we want is we want to show the left-hand side equals the right-hand side. But check this out. What is u? U is log base a of a. What is v? V is log base a of b. So I'm going to write that. This is log base a of a plus log base a of b. Hey, that's what we wanted. If you look at this chain of equal signs, we started with the left-hand side of law 1, and we showed that it equals the right-hand side of law 1. And that's what we wanted. We showed that the two sides are equal, and that's the end of the proof. Sometimes at the end of a proof, we will draw a little shaded in square or some kind of symbol to indicate that the proof is over. You might see that in textbooks. So all of this explains why this law is true. Where did that plus sign come from? Ultimately, it came from this, I think a real key step was using this property of exponents. That's where the plus sign came in. All right, so we're going to do this sort of thing for 2 more laws, and then we will start using the 3 laws to solve problems. Law 2 says a logarithm base a of a quotient, a over b. So law 1 was a product, a times b. This is the quotient, a over b. It's actually going to equal this minus this. We're going to prove that this is true, but I'll give you a minute just to take a look at that. Does this seem plausible? Does this seem reasonable? I want to say that in a weird way, I think that this does seem reasonable, and I'll tell you why. We already established that law 1 is true. Law 1 had a product on the left-hand side, and we wound up splitting up the logarithm with a plus sign in between. Now I'm looking at the way law 2 is stated. Instead of a product, it has a quotient, so instead of multiplying, it's dividing. And I feel like dividing is the opposite of multiplying, in a way. And I feel like the minus sign that we get is the opposite of this plus sign that was here. So in a sort of roundabout way, I think it makes sense. It's, opposite type of operation on the left, opposite type of operation on the right. Now, what I just said is not really a proof, but I'm just saying I think that it seems plausible that this could be true. For this proof, we're going to use a trick. This trick would be hard to come up with from scratch, I think, but once you see it, Hopefully it'll all make sense. I'm going to say trick. What is log base A of this expression? Like, what is this thing equal to? And I'm going to answer this. I'm going to say, usually in a proof, we wouldn't like have a question mark. You could probably rephrase what we're going to write here in a more formal way. But this is pre-calculus, so I think that it's okay to be a little bit more casual with our proofs. Let's see. All right, this expression equals, well, one thing it equals is log base A of A. Like if I just canceled B over B. That's simpler, right? Just cancel B over B. And so it equals that. There's another thing that it also equals. I could say that maybe I look at this and think of this in terms of law 1. Because we have a product, we're doing a logarithm of a product. Law 1 says that we should be able to split this up. Now, whether or not this is helpful, we will see. But that certainly is true according to law 1. So this weird looking expression equals log base A of A, and it also equals this whole thing over here. Well, if this thing equals this right-hand side, and it also equals this right-hand side, then those two right-hand sides must equal each other. So, log base A of A must equal this other stuff. They must equal each other because they were both equal to that weird expression. Log base A of A equals this. It looks close. It looks similar to law 2, right? We're trying to prove law 2. And I'm gonna say that from this we can rearrange it. From this, we like to write sentences when we write proofs. From this, we subtract log A B from both sides to get, look what happens if I subtract that from both sides. I get log base A of A minus log base A of B equals log base A of A over B. And that is exactly what we were trying to prove. That is law 2. So we started with this weird trick, but the final outcome that we got is a formula that we call law 2. So that's the end of that proof. It's kind of a sneaky way of proving it. Notice that I think a key step in proving this is that this proof relied on us already having law 1. So we proved law 1, established that it's true, and then we can use it to prove other things. And that's how math goes. I mean, this is pre-calculus. I'm expecting that most of you are probably planning to take calculus, and you're going to see this pattern that, you know, in math you prove something, and then you use it to prove the next thing, use it to prove the next thing, and we keep building up all these building blocks of math until we get calculus and more. A nice logical order to it. And it might be possible to prove this without law 1, but then we would need a different strategy. All right, I said there were going to be 3 big laws. The first one seems to be about a logarithm of a product. I think that this might sometimes be called the product rule for logarithms. And down here, this one was about logarithm of a quotient, and I think sometimes it's called the quotient rule for logarithms. If we did products and quotients, what else are we going to do? This next one, law 3, I think is sometimes called the power rule for logarithms. and it says log base a of a to the c equals c times log base a of a. And we'll prove this also. Remember, up above, we already established lowercase a is any base. A, B, and C are real numbers. And A is positive. Capital A is positive. All right, so this is cool. This says that if you had a logarithm, if you had something, an expression of that looked like this left-hand side, the C looks like it can be kind of pulled out as just a constant out front, which might seem surprising. I mean, it was an exponent, and now we're pulling it out front, and it's not an exponent anymore. So the way we're going to prove this is going to be similar to how we proved law 1. It's actually going to be even simpler than that. We're going to let u equal log base a of a. That's something we did in the proof of law 1. And I'm going to say then a to the u equals capital A. But we don't even need v. We don't need, like, that other stuff. All right, so let's see what happens if we start with the left-hand side of the law. And, you know, just to be clear, in math, when we prove things, I can't use this formula. Like, you can't prove law 3 by using law 3. That wouldn't make sense. That wouldn't justify anything. I can't say, let's use law 3. We don't know that it's true until we prove it. It would be like trying to write a definition that, you know, refers to itself. So we can use law 1 and law 2 if we want. We could use properties of exponents if we want. Let's do an equal sign. Let's see. We could use this a to the u thing. So what I'm going to do, capital A to the c, capital A is a to the u. So let's write this as a to the u to the c. How about that? Now I see a rule of exponents that I think would help. We could make this a to the uc. That's a rule of exponents that says if you're going to raise to the u and then you're going to raise to the c, you could just raise to the uc. All right, do you see what step we're going to do next? I am going to use, let's move this page, this guy, this thing, right? This thing that I wrote at the top of the page from the previous video. This is going to help us. Log base a to the something. We have that here. Log base a to the something. This is going to just equal uc. Does that get us what we want? Well, it does, because look at what lowercase u is. Lowercase u, we said, is log base a of a. So this whole thing is c times log base a of a. And that is the right-hand side of law 3. That's what we were trying to prove. We started with the left-hand side. We have a chain of equal signs, and we wound up getting the right-hand side. So it seems that we proved this without even needing law 1 or law 2. So I guess we could have done this one first if we wanted. All right, so this section is called laws of logarithms, and those are the 3 big laws. There's one additional rule that we might see towards the end of this video, but these are the 3 big ones. Now, we can use these laws to evaluate and simplify expressions involving logarithms. So let's do some example problems. I'm going to say evaluate and simplify. I'm going to do these without calculators. So I think what I'll do is write a few problems, and then maybe I'll do the first one, and I'll ask you to try some on your own also. Log base 3 of 18 minus log base 3 of 2. log 5 plus log 20, and log base 2 of 16 to the 1000. So how about this? I'm going to do part A. After I do part A, I'll give you a minute to try to do part B and C. Okay, so part A is two logarithms with a minus sign in between. The idea is to look at part A and identify that that looks like the right-hand side of law 2. So I think law 2 applies. And if it looks like the right-hand side of law 2, then it must equal the left-hand side of law 2, which says we can combine these two logarithms into a quotient of 18 over 2. When there's subtraction, it combines into division. 18 over 2, we know, right? 18 over 2 is 9. So now we've turned it into just log base 3 of 9. Hey, wasn't that one of the warm-up problems? Look at that. Warm-up problems. We did this. At the bottom here. Log base 3, 9, we said was 2. So we have the answer here. This is going to equal 2. All right, so I'd like to give you a minute to try part B and C. This would be a good place to pause the video, take a couple of minutes, and then you can hit play and I'll talk about it. All right, I am going to copy this down, and we'll see what this equals. Oh, this looks like law 1. This looks like the right-hand side of law 1. And if it looks like the right-hand side of law 1, then it must equal the left-hand side of law 1. By the way, this just says log 5, log 20. There's no base written. And when there's no base, remember that that means the base is 10. This is going to be log of 5 times 20. In other words, this is log of 100. Because the base is 10, I think we saw this problem in one of the previous videos, maybe last time. The base is 10, so this is like saying 10 to what power equals 100, and that answer is going to be 2. Exactly 2. Oh, by the way, I'd like to mention that by itself, log 5 is kind of hard to figure out what it equals. It's one of those weird decimals. And log 20 by itself is hard to figure out what it equals. But we now know that log 5 plus log 20 is exactly 2. So you don't have to figure out the individual parts. Finally, log 2, 16 to the 1000 is an enormous number. I don't even want to work with 16 to the 1000. You know, I don't want to figure out what that is. And luckily, we don't have to. We use law 3. Law 3 says that the 1000 is going to come down front as just a constant outside. You can only do that because this is a logarithm and because that's a rule that we've established. So that's kind of the capital C from law 3 getting moved out front. And now we just have this little question of figuring this out. Log base 2 of 16, 2 to what power is 16? And that's going to be 4. So we have 1000 times 4. Answer is 4000. So those are some types of problems you could see. And it just so happens that I set this up so that we got one problem for each law. All right, let's keep going. Let's look at some other problems. What we just did was I said evaluate and simplify, and we did evaluate them. We got like 2, 4,000. That's as simplified as you can get. Besides that type of problem, you could also use the laws to expand or combine expressions. Maybe some things where you don't just have numbers, but you have like variables and letters. So this time I'm going to say expand the following. Expanding is kind of the opposite of simplifying. Again, I'm going to put 3 problems, and again, I'm going to do the first one, and then I would like you to take time to try the others. There's B. You know, because a big part of learning math is doing it on your own. Even if you have to struggle with it a little bit, that's all part of the learning process. So I'm going to do part A. I'll give you a chance just to copy those down if you're writing those down. But, you know, I need to show you what I mean by expand. Solutions. So with part A, I'll show you what I mean. We have log base 6 of x squared y. Now, I would say that this kind of looks like the left-hand side of law 1, because we're doing a logarithm of something times something, right? X squared times y. So I could expand this to be log base 6 of x squared plus log base 6 of y. And that's considered expanded because now it's 2 logarithms instead of just 1. However, there is one more thing I'd like to do. In the effort of expanding, it's considered to be even more expanded if I take this 2 and pull it out front by law 3. And now it is as expanded as it can get. And I'm going to put a box around it, and that's the answer that we're looking for. It's equal to the original thing, but it's fully expanded. So I'd like you to pause the video, try part B and C, and then check back with me and I'll go over them. Okay, first one, part B, ln of, we have a cube root to deal with. The cube root of A, all of that's over BC. What I'm thinking here is this is a quotient. I'm thinking law 2. Law 2 is for when you have a logarithm of something over something. So by law 2, this should be ln of the numerator minus ln of the denominator. I'm going to write, just for our notes, that was by law 2. Okay. Now, what can we do with this? I think I'm going to do 2 things at once, if we're okay with that. The cube root of A, I prefer to think of that as a to the 1/3. That's the same thing. Cube root of a to the 1/3. And ln of BC, I'm looking at that as a product, like B times C. And I'm thinking, I kind of want to use law 1, right? Law 1 says split this up with a plus sign. The thing we have to be careful about is this minus sign out front. If we split up the ln BC, if we expand it, we need to make sure that the minus sign stays in front of the whole thing. So I am going to add parentheses here and do ln B plus ln C. So what I'm suggesting here is that the parentheses that I added, you either need the parentheses or you need to distribute the minus sign, which I'm going to do in the next step. We used law 1 here. Next, a to the 1/3. This looks like a candidate for law 3. Law 3 says that when you have a power inside a logarithm, you can pull it out front. Look at that. 1/3 ln A. And now I'm going to distribute that minus sign. So minus ln B minus ln C. So besides distributing the minus sign, I guess the other significant thing I did in this step was I used law 3. So look at that. We got a problem that used all 3 laws in the same problem. And it was in base E, so everything was ln to make things extra interesting. And that's the answer. I think that the most common mistake that I see on this type of problem is students would have a plus sign here. But this needs to be a minus sign because remember, we were subtracting all of ln BC. You're not just subtracting part of it, you're subtracting all of ln BC. So I did parentheses to make sure that that was happening. And I distributed the minus across the parentheses. By the way, in those previous problems we did, the previous set of 3 problems where we were doing evaluate and simplify, in those problems it felt like we were using the laws to combine things, and now we're using the laws to expand things. But I guess what I want to say is you could kind of check your answers. Like you could look at this as a problem and say, what if I try to use the laws to combine this as much as possible? And do some steps, and you should get the original problem. So you can kind of check your answer, but it would just take a bit of work to do it. And then for part C, I think for part C there might be 2 different ways to do it, but I gave you log square root of xy, and I asked you to expand. The way that I'm thinking of this is, you know when we had the cube root and I said let's rewrite it as a to the 1/3? I'm going to rewrite this as xy to the 1/2, because, you know, raising something to the 1/2 is the same as taking the square root. I like that because then I could pull the 1/2 out front. This one just says log, by the way. There's no base, so that means the base is 10. Log xy. Log xy is log 1 telling me to split it up into log x plus log y. Notice that I kept the 1/2 out front. And the 1/2 should be attached to both pieces. So 1/2 log x plus 1/2 log y. And that's a good answer for that one. I don't think we can expand that anymore. That's how I solved it. If we were doing this in person, I might ask if anybody solved it a different way. I'm going to tell you like one other idea that I had is you might look at this and you might think of it as log of the square root of x times the square root of y. Because that's technically equal, splitting up the square root into the 2 pieces. And then you might apply law 1, the product rule, because you could say now it's like a product of this times this. So if you do this, you'll do a few steps, you'll wind up at the same answer. I don't think it would be any more work or less work. I think it's just same amount of work. All right, let's continue with the problem solving, because I think it's good to see lots of these. So what we just did would be considered expanding. Instead of expanding, sometimes it's useful to go the other way around and combine expressions using logarithm laws. We did a little bit of that when we were evaluating and simplifying, but let's see some problems that don't just equal some nice whole number. Like those ones we did before where the answer was 2, the answer was 4,000. Let's see some that don't equal nice, neat integers. So we're going to try to combine the following. What have I got here? I've got 3 of them. Let's do 3 of them again. I'll do the first one. We'll do the same thing. We're a set of 3 problems. Why not? So you can wait till I write them all, and then I'll do part A. R ln x minus ln y plus ln z. That's a lowercase z. Sometimes in math we will draw like a little slash through a z to make sure that it doesn't look like a 2. All right, there's 3 problems. I want to do the first part for us. Okay. I'll do part A. What have we got? I think log base 2. All right, you know what? How about this? The log base 2 of 3, let's just keep it the way it is. But the other part, 2 log base 2 of 5, we could bring that 2 inside as an exponent. I guess in the other problems we were like pulling the exponent out, but we could bring this in and make this log base 2 of 5 squared. By law 3. Or in other words, that's a 25. Now it seems like a perfect candidate for law 1, which says we can combine this into 3 times 25. 3 times 25 is 75. Can we simplify this any further? That's the question. In the previous problems, we would get to something like this, and then we would find that it equals 2 or it equals 3 or whatever. However, this problem is asking us, like, 2 to what power equals 75? We can't really do that by hand. So we stop here, and we say we did combine it as much as possible, and that's the answer. All right, so before you try part B and C, I'll just tell you the general idea is you simplify logarithms to numbers when you can. So when it's like log base 3 of 9, that one I would expect you to simplify it to 2. If you see log 100, I would expect you to simplify it to 2. But log base 2 of 75, that's not going to be a nice whole number. That's not even going to be a nice fraction. It's going to be a really messy decimal. 2 to some power equals 75. 75 is not even close to being a power of 2. So we just leave it as this, and we say we did as much as we can by hand. All right, so now's a good time to pause and try part B and C, and then I will talk about them. B and C, let's try to do part B over here. All right, I'll copy it down. R ln x minus ln y plus ln z. We would like to combine things. So we have, you know, the r out front. We've got a minus. We've got a plus. And there's sort of the question of like, well, what do we do? What do we do first? And I think, you know, order of operations says multiplication kind of happens first. This is r times ln x. So let's deal with that piece first and make this x to the r. That's good. Now, next, order of operations. What do we do next? Do we deal with the minus sign first, or do we deal with the plus sign first? And this is a place where I often see mistakes. It does matter which one we deal with first. We would get different answers, and one of them is right and one of them is wrong. We need to deal with the minus sign first, because it's to the left. When you have pluses and minuses, you go from left to right. In order of operations, plus and minus happens at the same tier. So you read from left to right. So we're going to merge these, is what I'm saying. We're going to use the law of logarithms that says this is ln of x to the r over y. And then we still have this plus ln z out here to deal with. You do the same thing when you're adding and subtracting numbers, by the way. Like, these are ln of expressions and variables. But if I gave you some little arithmetic problem like 5 minus 3 plus 2 or something, you would do the minus sign first because it appears to the left. All right, now we can merge all of this using the rule for the plus sign, and we get ln x to the r z over y. And that is as combined as you can make this, and that's a good answer. That's what we were going for. And by the way, when I say we had to do that minus sign first, that's because there's no parentheses. If there were parentheses in the problem, then that might change things. Order of operations gets affected by parentheses. So always follow parentheses first. All right. Problem C. 3 log 2 plus 2 log 3. Individually, these pieces are hard to figure out by hand. Base 10, like 10 to what power is 2, 10 to what power is 3. We don't really know, but let's not try to deal with that. Let's just try to combine. So I'm going to bring the 3 inside as an exponent, and let's bring this 2 inside as an exponent. Well, 2 to the 3 is 8. Right? 2 times 2 times 2 is 8. And 3 to the 2 is 9. 3 times 3 is 9. And this looks like a great candidate for log 1. We have log of something plus log of something. So we combine it into log of 8 times 9, which is 72. And then we have to ask ourselves, can we simplify this? You know that earlier, I keep bringing back like old sheets of paper, but I'm going to show you this again anyway. Earlier when we had log 100, we were able to simplify it to 2. So log 100 is 2. But log 72, we can't really simplify by hand. And why is that? It's because this is like asking us 10 to what power is 72. Well, I'm going to put a box around this and say this is the most simplified that we can do this by hand. I'm not even really interested in what it is on a calculator. In this class, we're interested in doing math by hand as much as possible. And log 72 is exactly the answer. That's an expression that is the answer. I guess we could approximate what it is. Side note, approximately. What is log of 72? I'm going to do the same kind of trick that I did once before. I guess it was in the previous video. We're in base 10. So this is like saying 10 to what power equals 72, right? Here, let's move this. Can we get like a ballpark answer? We could try different powers. We could say like 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, and we might be able to figure out like which one of these is it closest to. 10 to the 0 is 1, then this is 10, 100, and 1000. So this is why we're able to evaluate log 100 and get an answer of 2. We're able to answer things like log 10, log 1000. But when it's log 72, well, it's somewhere in the middle here. It's somewhere here. 72 is somewhere between 10 and 100. So that means this answer we're looking for is somewhere between 1 and 2. So log 72 is 1 point something, because I know that it's between 1 and 2. This was a side note, but I do think that this is sometimes helpful for, understanding that logarithms are not just some mysterious entity that we plug into a calculator. It's the exponent that would go here. That's all it is. Okay. So we've done a good amount of problems. What else can we talk about here? All right, we've got a couple more things to talk about. One thing that I would like to do, that I always try to do when I teach logarithms, is I want to tell you some common mistakes to watch out for. So I was going to say I was going to show you 4 common mistakes, but I'm gonna make it 5. 5 common mistakes to watch out for. All right, number 1. I usually don't like writing things that are wrong. So if I'm going to show you mistakes, I might have to write some things that are wrong, but I'll try to make it clear what is right and what is wrong. All right. Log base a of x plus y does not equal log base a of x plus log base a of y. That left-hand side does not equal that right-hand side in general. I mean, you might be able to find like a, if you really want to nitpick, there might be one example where this works. But in general, this doesn't work. These are not equal. I'm going to show you an example. For example, let's say I had log of 4 plus 25. The question is, does that equal log of 4 plus log of 25? Are these things equal to each other? Well, on the left, I could just say this is log of 29. 4 plus 25 is 29. On the right, we would use law 1 to say this is 4 times 25, which is 100. So I hope that you can see that these are not equal to each other. One of them is log 29, one of them is log 100. So watch out for that kind of mistake. You can't split up a log in that way. Almost looks like law 1. It's kind of like a mistake version of law 1. Similarly, another common mistake to watch out for is if you have a log of something minus something, that is not equal, put a big X through this, that is not equal to log base a of x minus log base a of y. And I don't have a specific example to show you for this one, but it's the same type of reasoning as the one above. That would be like a mistake version of law 2. The third thing I have, I guess, is kind of like a mistake version of law 3. So maybe it's good that we're doing these in this order. Parentheses, log base 2 of x cubed is not equal to 3 log 2x. Now, this one is a little tricky. You might say, wait, isn't this law 3? What makes this not equal is the parentheses. The parentheses mean that this exponent is on the outside, and we're not just talking about x cubed. You know, if it was just x cubed, with like the 3 was on the inside of the parentheses, that would be a different story. But because the 3 is on the outside of the parentheses, you can't do this. So watch out for that. Common mistake number 4 to watch out for is if you have something like log 6 over log 2, that is not the same as log of 6 over 2. Can't just say, oh, there's a log 6, log 2, just, 6 over 2. Also, log 6 over log 2 does not equal 6 over 2. You can't just cancel log over log. It looks like you see like a log and another log and you just want to cross them out, right? You can't do that because log is not a number. We can cancel a number divided by itself, but we can't cancel a function. Like, that's not a number. That's a log of 6, log of 2. So it would be wrong to cancel them out. And the 5th one on common mistakes to watch out for is that, how do I say this? Log and ln should never appear by themselves in an answer. For example, okay, this is one that I really don't like writing. I say that it just it gives me a weird feeling to write things that are bad notation or just wrong. But I think, it's good to know what things to watch out for. Let's say you were working on a problem and you got an answer and you said, my answer is 5 plus ln. This is always wrong. Okay? Because we never just say ln. It's always ln of something. It's always log of something. There's always a number attached to it. Okay? If you say 5 plus ln, it's kind of nonsense. It would be a little bit like, if I could make an analogy, it would be like having a square root symbol with nothing underneath it. Like 5 plus the square root symbol. You'd look at it and you'd say, square root of what? Put a number under there. So if you have something like an ln by itself, or a log by itself, or a log base 2 by itself, the answer would have to be wrong. There has to be, it's a function, so it has to have an input. So hopefully that was helpful. All right, we do have one more thing to talk about for this section. You know how at the beginning of the section I said this was called laws of logarithms and there were 3 big laws, but I think I said a couple of times that we might see one additional rule towards the end of the section. It just kind of gets pushed off to the end of the section. It's maybe not as important as the other 3, but we have something called the change of base formula. This will be our last topic for this section. And we're going to derive, this is going to be another formula, and we're going to derive it. So first of all, let's say we're given y equals log base b of x. You know that typically we've been working with a base that's called a. In this little discussion, I'm working with a base that's called b. It's no big deal. Let's suppose that a is some other number, you know, greater than 0, not equal to 1, some kind of base. All right, I'm going to use this to derive a little rule. The idea is there some way that we could convert something in base b to something in base a? That's the motivation here. Because if you look at laws 1, 2, and 3, it's kind of base A, base A, base A. The base never changes, and maybe that's a good thing, but maybe there are some circumstances where you would like the base to change. Maybe you have something in base 17, and you say it would be more convenient if that was in base 10. So is there some way that we can convert? What we're going to do is take this and say that this means that b to the y equals x. That seems fair enough, right? B to the y equals x because of this. I am now going to take log base a of both sides. We're doing this to derive something, so we are headed somewhere with this. You might say, is it okay to take a logarithm of both sides? And it is, as long as we do the same base. Log base a, log base a. You can do that to both sides of an equation. Technically, the reason why it's okay to do that is because it's a one-to-one function. Generally, with one-to-one functions, it's okay to do it to both sides. All right. I'm going to apply law 3 that says the y can get pulled out like this. Okay, how does that look? Next, I'm going to solve for y. Y is the right-hand side divided by this thing. So I just divided both sides by that denominator there. So what is the result of this? What is the result of all this? So I'm going to circle a couple of things to point things out. We started with y equals this, and we ended up with y equals this. If y equals both of these things, then these things must equal each other. So the result is that log base b of x equals log base a of x over log base a of b. And this is what's called the change of base formula. I'm not going to write it again. I wrote it above. This is the change of base formula. So does it really let us change from one base to another? Sort of. I mean, the left-hand side is in terms of base b, and the right-hand side is in terms of base a. It just has a little bit of extra stuff going on. Let me tell you one reason why this is useful. And that is that some calculators only have buttons for log and ln. You know, like if you have a scientific calculator or a basic calculator, it might have buttons for log and ln. And maybe you have like some expression that's like log of base 3 or log of base 4, and you're looking at your calculator like, how do I do something with base 3 or base 4? Well, one thing you could do is you could use the change of base formula to turn it into one of these more convenient bases. So you could use the formula to rewrite log base b of x. I'll just say with a more convenient base. and I'll show you this. Example. Let's say I want to know, with a calculator, what is log base 4 of 7. Now, I have a scientific calculator that I like. I think I've shown you a couple of times. I've had this for a few years. I like it. I actually don't really care for the TI graphing calculators. I find I don't have much use for them. I like scientific calculators that have about this much stuff on them. I think that's a pretty good amount. Anyway, this calculator does have ln and log on a button, but it turns out that on this calculator, if I press that button, it kind of cycles through ln, log, and then it gives me an option to put in whatever base I want. So I actually could do a base 4 on this calculator. All right, I could get an answer. But I said some calculators don't have that option. Some just have log and ln. So what you could do is very quickly with the change of base formula, you could say, if I wanted to rewrite this in terms of base 10, I would say A is going to be 10. You have to figure out what X is and what B is. This would be log base 10 of 7 over log base 10 of 4. And that's true. That's actually equal to that. And then on your calculator that can do log 7 and on your calculator that can do log 4, you find them. This is approximately 0.845, something, something, something. The one on the bottom is approximately 0.602, something, something, something. And altogether, it equals 1.403677 something. Calculator couldn't do base 4. We turned it into something involving base 10, and then we were able to get the answer. Or, what if you say you don't like base 10? What if you say you like base E? You could do this. This is also going to work. Say I've got a calculator with an ln button. I want to do this as ln 7 over ln 4. You figure out ln 7. You figure out ln 4. This looks different, right? It looks like maybe you're worried that this is going to be something different because above we had like 845, 602. This looks different, but actually when you work out the quotient, the ratio here, it still equals the same thing. So that's pretty cool. It looked different for a second, but it's the same thing. And you might say, well, all right, why don't you just get a calculator like mine that has the... Why don't you just get a calculator that can do whatever base you want? And that's, that's fair. But one thing that I want to tell you is sometimes calculators that let you choose an arbitrary base, sometimes they are doing this behind the scenes anyway. Like I might tell it I want base 4, and it might be using the change of base formula without me knowing it, because it's more convenient for a calculator to just store tables of log and ln. So that's kind of what they do. Computers and calculators will sometimes have like a big table of values of like what's log 1, log 2, log 3, log 4, ln1, ln2, and like have a huge table. And then if you wanted something in a different base, it uses the change of base formula and looks up these pieces on the table and gets the answer that way. So the point is, somebody had to program that, and it's a cool thing to know. I think in calculus, I've also seen one or two other uses of this formula. That this could actually be used in some other ways, maybe to like derive some other rules and stuff. but it's a little bit less important than the law 1, law 2, law 3. Those are kind of the big deal for the section. All right, so how was that? So we have learned the laws of logarithms. We also had some properties in the previous video. Don't forget those. So now we know a bunch of different things about how logs work, how you can simplify them, combine them, separate them, things like that. And, we did some example problems in this section, so you should be ready to do those types of problems. I'll tell you that in the upcoming videos, in the next one, we're going to look at exponential and logarithmic equations. Now, we've been looking at functions and we've been looking at expressions. The difference between this and equations is that when we get to equations, we're going to have like solve for x, where x is in the middle of a logarithm or something like that. So that's where we're headed. So we need to be good at manipulating logs like we did in this video. All right, and then I think 2 videos from now, I think we're going to have a section that's a short section just about real-life applications and word problems involving exponents and logs. Okay, so that is it for now. Take care, everyone. Hope everyone's having a good one, and see you next time.